Welcome to the lecture on implicit modeling within the course on computer graphics at KAUST. Today we will be talking about implicit modeling. Implicit modeling often takes in some analytical representations of geometry and turns them into a surface which we can then display. And we have already somehow worked with implicit representation during our ray tracing lectures or the assignments. But during this lecture, we will expand upon the modeling opportunities which the implicit representation offers. Besides the implicit models, we have also parametric representations like parametric curves, which we have covered, but also parametric surfaces if we expand the notion of the parametric curves into 2 dimensions and create 2-dimensional manifolds parameterized by 2 parameters. And then we have triangular representations, which are approximations of a certain shape with triangles as primitives forming larger meshes. In implicit modeling, we will be having some functional representations most often, where the advantage is that we can very flexibly change the topology of certain objects. So imagine, for example, water droplets. If they would be represented as spheres or of triangle meshes, and now we would like to join these 2 water droplets into a bigger water droplet, then we will need to perform a remeshing because this topological change will require that process. Similarly, for parametric representations, such a change of topological state will not be very easy to handle. But here, the implicit representation is a very favorable because it directly supports such changes. Unfortunately, it is quite a computationally demanding representation. Therefore, for interactive purposes, it has not always been the winning strategy. It contains a certain graphical geometric primitives in the scene, which are representing some kind of a skeleton, if you like, and then these skeletons are defining a particular function in space. And we are interested in this functional evaluation, which then defines us the surfaces. If we have several objects, we can perform blending of these objects together by simply summing up this function in space. So you can imagine that implicit representations defines you some values in 3D space or 2D space, depends on the scene, and this value, based on the value, we will either be defining whether we are outside some object, whether we are inside some object, or whether we are directly on the surface of that object. We can extend the CSG operations, constructed solid geometry operations, for the implicit modeling very straightforwardly. The implicit representation, as we have a functional evaluation everywhere in the space, we can easily define whether we are inside or outside of an object, which might be very beneficial for particular applications. And last but not least, we can relatively easily calculate the gradients because the gradients will be defined simply by the derivatives of our implicit modeling representation, by the formula. So we simply derive the formula in each spatial dimension, along each spatial dimension, and then we will have our gradient value, which we can calculate for each position in space. So the implicit representation can be defined as through some spatial primitives, and let's just here define one point in space which defines our implicit model. And then we define a certain function, d, which is the distance function from that point. So this is the point, and here we have a certain distance function. So 1, so this could be the distance 0.5 here, this could be the distance 1, and etc. And this distance is an input value into a next function, which is the gi, which is the fall of filter function, which could be differently defined for various purposes. It could be just a simple tent function, which will be rather having some discontinuities in the derivatives and in illuminate. We will see it in an illumination, or we can have more smooth functions. Jim Blin, who has somehow introduced implicit representation to graphics, has been using the kernel fall of filter function, which was just an exponential function, a Gaussian function, which was then defining based on a particular distance. So let's say distance 0.8, we will have some value which is reasonably close to 0. At the distance 0, we will have the value 1. So directly at our skeletal elements of our implicit representation, we will have the value 1, and then we will be decreasing this value based on how far we are from this skeletal element. So this is a implicit representation function, which for each skeletal element, we will be defining first the distance, and then this distance will be the parameter or input value into this fall of filter function, which will then define us a particular value. So maximal value will be at the skeleton, and there will be a gradual fall to 0. If we look at the Blin's kernel, the Gaussian kernel, it has an infinite support, so it's not 0 anywhere. For practical purposes, it is advantageous if we have some fall off to 0, and at some distance, like distance to 1, we will have value 0, and for larger distances, there will be a value 0 as well. So we can see here there are some polynomial functions which are used for the continuous fall off, like the metaballs, or soft object functions, or a Weibull function. These all are smooth and are 1 at the skeletal element and are 0 at the distance 1. Now, let's have a look at how we can define an implicit surface out of this, or an implicit curve in 2 dimensions. So let's have a first one point in space. We'll call it P0. And this point has a distance. I'll just draw Euclidean distances. This will be 0.5 distance. This will be distance 1. And if we use, let's say, the metaballs, at 0.5, we will have a value which will be approximately 0.4 or 0.3. So after applying the fall of kernel, then this distance, so I write here d equals 0.5, d equals 1. And here, at this distance, f 0.5 equals 0.35, let's say, and d equals 1, f1 equals 0. And for the skeletal element, so d equals 0, f0 equals 1. So we understand this sort of a potential field which is decreasing based on the distance from our skeletal elements. Now, this was just one element, and if we then decide to display it, we can, for example, say that we are interested in tracing a functional value, let's say f equals 0.2, and everywhere where the value of our metabol's kernel, for example, will be 0.2, so this is the distance 0.4. If I am not, so this is the distance 0.4, then we are 0.2 will be somewhere here. So this is 0.7. So the distance 0.7 is maybe somewhere here. So this is f equals 0.2, and we are then interested to trace a surface. So let's trace a surface of this one skeletal element, and this will be the implicit surface of this element. Well, we can change our value which we want to trace. It can be also f equals to 0. And if it will be f equals to 0, then we will be tracing this distance. Our surface will be larger. So depending, this is a parameter for our implicit representation, which functional value we are interested to trace. Now, let's have a look at, because we have just so far one point, that's not too great a representation, because we can only represent the spheres or circles. But now let's put one more point into this representation. So we have here P0, as I said, and now let's put point P1 here. And this point P1 will have also some distances. So this is 0.5, and this is this is distance 1, d equals 1, and d equals 0.5. And now we will be interested in, again, functional value of, let's say, again, f equals 0.2, but not of just the one skeletal element, but of the entire function which all skeletal elements are defining. So here we can see sum that at each spatial position, there will be now at each spatial position, let's call it P here, we will be summing up what is the functional value F1 or F1, let's say, at P plus F2 of point P. So this will be the value, and we will, as we can see, that these two functional values are overlapping. We can see that, for example, at position which is outside 1 for the P0, there will be only contribution, if at all, from the P1. So, for example, at this position here, we have F1 will be equal to 0, but F2 will be not equal to 0. The F2 relates to the skeletal element P1. So, and then there are some regions where this function is overlapping. So, for example, if we are now interested in f equals 2, then it relates to the distance 0.7. So let's draw around the P1 also 0.7, which is somehow something like this. And now we can see that the 0.7 is drawn here like this. But now we are now adding the one, once we are intersecting this blue circle here, we will be adding the functional value of one function with another one. And therefore, there will be increase of the values. And we can see that we will create here some kind of blend. So there, through the sum, we are creating a blend of these two um, uh, potential fields of the 2 points which are forming the skeletal elements of our scene. And of course, we can have more of such points, skeletal points, creating us more and more complex representations. In molecular visualization, Jim Blin actually introduced this representation to define a smooth surface of molecules. Molecules we are used to see as a set of connected spheres, but their surface is not necessarily a rigid balls, but can be interpreted or abstracted as a more smooth surface. And therefore, instead of having such concatenation of spheres, we can define it as a more smoother surface, something like this in this case. So this is the way how the implicit models can generate us smooth representations and can nicely support topological changes. We can see very nicely on the rendering here what is the behavior of our implicit representations. We can see that in our case, we are dealing with two skeletal elements here, 2 points, and the distance function serving as an input to the filter fall off function is defining us some potential field around these skeletal elements. And we can trace then a surface at a certain value of this functional value of our implicit representation. And now we will be bringing our points closer and closer. So we are decreasing the distance between points along going from top to bottom. And we can see that there is a smooth blend created. So instead of these points being, these surfaces being disconnected until they start to intersect, and the intersection will be not smooth, will be continuous, C0 continuous, but not smooth. There is a smooth blend. And this is caused because we are now summing up the potential fields of both of these two balls. And then the sum will be then traced along a certain value of the filter or the value of the implicit function. And we call this value an iso value. And the surface which it is forming is called an iso surface. So, and this image shows you an iso surface of the entire field, not of one skeletal element, but of all skeletal elements, which are 2 in this case. So what you can see that with the decreasing distance, this blend is smoother and smoother, and at some point we are generating some ellipsoid representation because these 2 points are very close to each other. And at the final position, the 2 skeletal points are at the very same position in space, creating a sphere again. The sphere, however, is bigger. Why is it bigger? Well, because we are summing up the functional values of both of these points, and therefore the value at each position will be the sum of these 2, so it will be higher than each element separately, as it was in the case at the very beginning when we had the 2 points too far away from each other. On the vertical axis, you can just see applying a various various filter fall-off functions like we had before. The Blin function is the left, in the middle there is metaballs, soft objects, and the Weibull function. And you can see that they are having roughly the same behavior. Somehow they are blending smoothly. However, when they start to blend is different for each of these kernels. So the blend is essential to be created through the summation of all the skeletal elements, which are then creating us the potential field. So the potential field of the entire implicit representation is the sum of potential fields of the individual elements. And the isosurface, which is then created, forms as the geometric representation. So if we would like to represent a water droplets, we can represent it with this implicit modeling representation, and we can see how these two water droplets will join into a larger water droplet exactly as we would like to have it. And the change is very natural for this representation and doesn't require any remeshing or other inconvenient operations which would be associated with, for example, triangular mesh representation. The gradient can be also defined for the entire function. So not only for one skeletal element, but for the entire implicit representation. We simply can calculate the partial derivatives along x, y, and z dimension. And if we have, we can either calculate it analytically, or we can calculate it by simply evaluating a function value at a certain position and then at some other position, and then find a change in these two positions, and that will define us the derivative, the gradient. So for example, if we have two dimensions and we evaluate a functional value at one point, and then we evaluate, so this is x and y, and then we evaluate the functional value at another point, then here we can generate the gradient for by subtracting one value from another, we can generate the x component at this particular location. Now we can also perform the same for along the y dimension, and then evaluate the component for the y coordinate. So this would be called forward differencing, and there are several schemes of how can we compute the gradient. The gradient is giving us a direction of which is the closest point to a surface of the skeletal elements. Oh, sorry, which is the closest point on the surface of our implicit representation. So if our implicit representation creates some kind of a circle like this, because there is a potential field emanating from one skeletal element, then the evaluation will be that we will have the gradient, which will be the value going towards our value at the particular location where we are tracing with some ISO value our ISO surface or ISO curve in the two dimensions. So we are defining the gradient direction, so the direction in which is the closest element on the surface. This is already grade information, and also the gradient gives us what is the distance to there. So because we evaluate the distance at each location, so we can therefore find out how far are we from this surface. If we are defining the partial derivatives and they are all C0 continuous, then the function itself will be C1 continuous. And the great benefit of having the gradient is that it can be used for defining as the normal vector at the particular surface position, which means that we can define the illumination at that surface position through this gradient evaluation. Keep just in mind that sometimes, based on the definition, we will simply need to have an opposite direction of the vector to the gradient direction. And of course, we will need to normalize the gradient in order to create a normal vector suitable for the illumination calculation. So our implicit representation is defining us a certain distance from a surface or from a skeletal element. So for example, if we have a certain point, we can define a so-called distance field from these points. And this distance field can be either considered from the skeletal element or from a particular surface, which this skeletal element and the fall of function and the distance from the skeletal element is defining. So let's say that we will be defining a distance field from a point. So this is obvious, so we can easily calculate what is the distance, Euclidean distance from a point. If we have, however, a line, then we will be calculating the minimal distance from our point to a point on a line. So if we have our point P is here and our line is here, then we are calculating the closest distance to a point, and this point will be the point Q. So this is the calculation how we calculate a distance field around a certain object. It's trivial around a point, around a line, it is reasonably easy, around plane as well. With more complex skeletal geometry, it might be more and more complex. So now we are extending the notion of skeletal elements from points to arbitrary geometry, really. It can be points, it can be curve, it can be surfaces, it could be even solids. Of course, the distance, if the point lies on the surface or on the skeletal element, defining which distance we are calculating, then the value will be 0. Imagine that we have a distance field from some implicit representation, where this will be our surface of our implicit representation. So we have our skeletal element, and we are tracing this f, let's say f equals 0, which means d equals 1 for the skeletal element. But now we are interested in knowing the distance from the surface point on this circle here rather than from the skeletal element. So the distance at some position here will be simply a distance to the surface. And as I said, it can be defined through this gradient information that gives us the vector, and also the distance can be obtained as well. Now, if we have a point inside of this surface, let's say here, then there will be also a distance, but we are often having the notion of something called sign distance. So we will have a negative distance value. This means that our object is that our point, which we are evaluating the distance from, lies inside of our implicit model. And if we are connecting the distances of from a certain some constant point, all points which have some particular distance c from a surface, we are creating, as I called it before, the isosurface, but also this is called a level set. So keep in mind that with this we can generate something like, if we have here this line on the top, we can generate a level set which will have equal distance to the line. So there is an equal distance here, 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 approximately, and so on and so on. So this is a level set, and we can see that it also creates a smooth surface or smooth curve in this case of 2 dimensions. So this is the notion of a distance field in our implicit representation. So for implicit representation, a key element is to have some notion of a distance. This distance can be either calculated explicitly or it can be also stored in some kind of representation. Like, for example, in a discrete representation, where you can have pixels in 2 dimensions or voxels in 3 dimensions encoding a distance to a particular surface. We will see how this can be calculated in a moment. This can be calculated with the so-called distance transforms. Why this is interesting if we have all the data available analytically anyway? Well, we do have for a lot of mathematical surfaces an opportunity of an analytical representation. But this is not generally the case. Sometimes we will perform scanning of a certain object, let's say in medical context, an anatomical scan of a human body, and then we would like to create an distance representation, an implicit representation of a certain organ, for example. And in such case, we do not have the analytical representation at hand, but we do have a discrete representation, voxelized representation, which we can then turn into a distance representation, but still defined discretely. And in such a representation, we will then have the distances encoded in each voxel. And through this voxel in neighborhood information, we can also then resolve the information about the gradient, or we can also interpolate the distance value between the sample values of our explicitly defined positions of the voxels. So finally, we can always convert an analytically defined representation into an discrete representation as well, because if we have a combination of analytical and discrete representations, the simplest would be to create a discrete representation and represent the implicit objects in a form of a distance field discretely defined on voxels. So with this representation, we can do pretty much the same thing as with the analytical representation, besides the fact that we might lose somehow a precision. It depends on how well is the spacing between the samples, how far is it, whether we are capturing the details of our representation or not so well. For the distance calculation, imagine that we have a certain object, and we would like to define a discrete representation of this implicit object. So with the distance transform, first of all, we have to decide on some grid spacing, which is, let's say, uniform. This can be also varying, but in most cases this will be the case. And then we will be defining the values of the certain distances. So for example, at the voxels, centers of the voxels, where through the voxel area passes our surface, we can define that the distance value is 0. So we will have a 0 value in all of these voxels. And then for assigned distance representation, we will have value -1 in all voxels which are inside the object, and then we will have a value 1 for all objects, for all voxels which are outside, just by step 1 from our voxels which are already tagged with the value 0. And then we perform another iteration to have the distance 2. And if our grid will be larger, we can define even larger distances. So there are several calculations approaches how this distance field can be calculated. Some are more efficient than the others. Those which are more performant, which are faster to compute, are typically more approximative distance transform methods, and those which are taking time will be more accurate. With increasing sample size, the resolution of our grid, we will have a better and better capture of our distance representation through samples, but we can generally reconstruct the representation from the distance representation quite well. The other way is to convert an set of sample data into an analytical formula. We will call this variational implicit representation, where we have some certain sample set and we are defining some formula which will characterize, which will be an analytical description of our sampled representation. A typical one will be the thin plates spline, which is known to be least curvy representation of surfaces or curves which are approximated through a certain sample set. So if you are hearing about a variational implicit representation, you will know that this is the input for this will be set of samples, and the outcome will be an analytical representation of such a surface, which you can then use directly for representing your implicit model. The next group of representations are the so-called convolutional surfaces. Now, if we had our point skeleton defined and it was defining as the distance was defined very clearly. And if we were defining with as a Euclidean distance, if we had our line, for example, in the case of line, we were defining the distance as the smallest distance, shortest distance to our skeletal primitive. And we can have the so-called distance surfaces or level sets, which will be defining as an isosurfaces with an equal distance. And convolutional surfaces are slightly different approach to the representation of our implicit models. The difference is that in a case of the distance surfaces, only one element on the surface sort of contributes to the position of the offset of the surface. However, in convolutional surfaces, if we will have a certain line, then one point is defining a certain value, potential field, another, its neighbors as well. So we will have certain potential field defined by all these elements, which will be then summed up. So we will, as we know, we will have a reasonably a little bit larger offset because of these contributions. But the advantage of such convolutional surfaces is that they will have a smooth connectivity of elements, and there will be minimal bulging effect. Imagine if we have three distance or level set representations of points like this. Then, in such a case, the sum of the elements, which is here, will create as a bulge. But for convolutional surfaces, as we are contributing from the neighboring values as well, then this bulge will be much less pronounced. And also, we could also consider that we will just have three different elements and there will be no blending between them. So the blending of the will be not, the blending operator will not be additive, but will be, let's say, the max value, for example, which will form a union of these elements. This will be nice on one hand, but on the other hand, it will create us a sharp border. So if we will have a union of three small line segments, as it is shown here, then the union will result into sharp borders here and not as nice smooth blend. Sometimes it might be desired, and therefore we will also use such a max operator. But if we use additive blending, then convolutional surfaces will result in a smooth transition between the individual line skeletal elements and will result into least of bulging. We can see an example of convolutional surfaces modeling here, where we have several elements. We have some line skeletal elements, which are curves in the space. And these convolutional surfaces will then have a certain filter kernel where all of these points along the line will be contributing partially to the value of and forming then the potential field of the entire space. And then we perform some ISO value extraction in order to represent these structures. So we can see that we have individual elements for individual fingers. Then we have some surface, which could be represented either as a set of triangles or maybe as a surface patch, as a parametric surface, which is the skeletal element, which is used then for the as a convolutional surface generator. And putting these two together, we will have a simplified representation of a hand. Now, if we put some additional skeletal elements and convolutional surfaces thereof, we can have a nice representation of tendons on top of that. And if we add some vascular structures and this bulging muscle between the index and the thumb, we can generate a realistic representation of a hand. If you will represent or model such a representation with triangular meshes, this will be a very difficult process to model, or with other parametric representations. However, with implicit representations and with convolutional surfaces, a representation of smooth surfaces like organic shapes is easy to model. So it's a great benefit for the modeler to use such surfaces as a means to model three-dimensional objects. In scientific visualization, sometimes these convolutional surfaces are used for representing the vascular structure. You can imagine that you have a vascular structure, maybe aorta, then you have some peripheral arteries, and these arteries are then further bifurcating into other smaller arteries and so on, forming a vascular tree. If you will extract the center line out of these vascular structures, then you will have a compact representation of the vascular tree, which is compact, but it's a little bit sparse because you don't know the thickness. And in order to gain the thickness of your vascularities, you can use the convolutional surface representation, which will then give you a notion of the vascularities. And there, where the vascular structures are branching, you will have a smooth transition and there will be not a hard edge. So this representation can be very good for representing otherwise difficult to represent objects which are extracted from anatomical scans. If we will use the scan directly, it will be very noisy. The vascular structures will be very, have many micro bulges, and we know that the vessels do not look like that the vessels are smooth. These bulges are originating from the noise of the acquisition, and therefore a convolutional surface will much better represent the smoothness of the anatomical vascular structures. For any implicit representation, we basically need the skeletal primitives, some distance metric, and the follow function, and then also the blending operator. Now, let's have a look at the distance function, how this can be computed. Well, we can have different skeletal primitives, and the distance can be computed based on what primitive we are dealing with. If we have point as a skeletal primitive, the distance calculation is trivial. If we have a line, then that we can use some linear algebra machinery to calculate that. And if we have faces, if we have curves, we can usually find some mathematical methodology in order to calculate the distance. Just to refresh our memory, how do we calculate the distance to a line from a point? So we have a point in space, which is, this is the point P0, and we would like to calculate the distance to a line, which is defined through a vector AB. Let's call this vector AB a small vector A, just that we have a little bit less of writing. And let's call this vector being the vector B. The strategy here is, in order to define the distance, is to find a projection onto AB, onto our vector A point C, which will be which will form an right angle between the AB vector and C P0. We know AB and P0, but we do not know the C, so we need to calculate the C. Once we have that, we calculate the vector CP0, and then we define its length, and that will be the distance from a point P0 to AB. Well, we see here what is the formula for that, and we might see directly that we are scaling the vector AB, the A as we call it here in the drawing, with some scalar factor. This scalar factor, let's call it S, is the entire fraction which we can see here. So the vector CP0 we can also call as vector B minus S scalar A. So this is the AC, is the SA, and B minus SA will give us this line segment CP0. Now this line segment is perpendicular to AB. So let's write that A vector dot product with B minus SA equals to, what does it equal to if it's perpendicular, these two vectors? Well, equals to 0. Well, for that, we can see that A, B equals to A, S. And from this, S equals to A dot B vectors divided by A dot A. And now let's have a look here. And we can see that our A and B are AB and AB0, and the denominator is a scalar product of A with itself, so AB squared is here the value. So this is how we calculated the S, and this gives us the scaling in order to find the point C from the vector AC, which is a scaled version of the vector AB. So this is the way how we can calculate the distance to a line. And for other geometric elements, we can find the distance in a similar analytical way, oftentimes. Now, we have seen as a skeletal primitives the point. Then we have seen a line, and keep in mind that we had this potential or this distance implicit representation through level sets, and the second was the convolutional surfaces. In the case of level sets, we were calculating just distance or the implicit representation from just one point, which is closest to the surface, and we were not contributing to the surface as a blend of all points on the skeletal primitive. That would be the convolutional surfaces. And with such methods, both the level sets or convolutional surfaces, we can generate a 3D objects out of a rectangle or 3D objects out of cube, out of circle, or out of two-dimensional disk, out of cylinder, or out of cone. So these all can be skeletal primitives in the implicit modeling framework. For each, we need to have the distance measure, and then we need to have a certain kernel which defines our follow function. Well, once we have that, we still didn't see any image, because so far we only described how the entire scene is defined, but not how we render it, how we display it. There are essentially two methods. One we could call a direct method, where we are ray tracing the implicit representation. And in this ray tracing, we would basically go through our space with a ray, and we will be evaluating the function. And by evaluating the function, we are looking for where do we intersect our desired value, where the fall of kernel will give us a value which is equal to the one we are looking for. Let's say maybe 0.5, or a value which is close enough to that. Often we need to resort to some kind of root finding methods, because otherwise we will not be able to find where the intersection is. So we iteratively are trying to find the point on the ray where do we have the intersection of our implicit surface with our ray. This is the direct method, and once we find that point of intersection, there we will calculate the gradient value, and on the gradient we will then use the normal for the illumination. The other method is indirect method, where we first transform our implicit representation into some explicit geometric representation, and then we are representing this representation in a much faster way using the traditional graphics pipeline. This, however, this approach will have a problem if we will have a very often changes of our geometry. As long as the geometry of our implicit blends stays constant, this might be a winning strategy because performance-wise, it will likely beat the direct rendering of implicit representations. However, if we are constantly changing our topology of the objects and so on, positions, and we always need to re-evaluate new surface and approximate it with the triangle mesh, then the ray tracing approach might be actually, the direct method might be beneficial. So, as mentioned, the ray tracing is casting the ray through our space, and we are evaluating at some sample positions what is the value in the space. And for this evaluation, we are using all the skeletal primitives which are around. There could be many, and these many we have to calculate what is their individual value at a particular sample position, and then sum this value up of all skeletal primitives. So with this, the complexity scales with the number of primitives tremendously. We can perform various compositing techniques. It can be either the sum, but for some objects, we would like to maybe not perform the sum, but a union or an intersection or a difference perhaps. So this all can be realized, and we can already see that we can perform some construction solid geometry operators on the implicit representation through performing the compositing not only as a summation, but other forms as well. Now, at some point, we hit the given, let's say, f equals 0.5 for as the sum of our skeletal primitives functions, and then but we hit something which is close to 0.5, not exactly. So we have to define some epsilon value, some range, which will be an tolerance for finding the surface. The smaller the epsilon, the more iterations we would need in order to find the more precise surface point. As I said, at the end, we are calculating the gradient, and with the gradient, we will obtain the normal for illumination. However, we can use the gradient also along this pipeline, because the gradient can tell us how far is essentially our surface, and that gives us a notion how far do we need to, can we skip on our ray. So imagine this is our ray, and our surface is somewhere here. Let's make the ray a little bit longer. So at my central point here, I am evaluating what is the distance to our implicit surface representation, and the distance will be this distance. So I know that there is no implicit object closer, and therefore I can just, my step can be, I can jump with my samples and evaluate directly here, because that's the distance along which, along the ray, there is for sure no implicit object along the ray. And this approach, with this kind of method of fast forwarding along the samples along the ray, is called sphere tracing. All right. So with this sphere tracing, we can then jump faster to the location of our ISO value, but sometimes it can also slow us down, and therefore we could have some minimal constant jump along the ray. And sometimes we jump over our ISO value which we are looking at, and therefore we need to then jump back by half. And through this iterative bisection method, we can find the approximation of our surface point quickly. In order to somehow manage the complexity, we can also organize our skeletal primitives into some kind of grid representation, so that we know that the one skeletal element is here, one is here, one is here, and maybe two or three are here. And if we are currently going along with our array, and then we know where the skeletal primitives are and what is their area of influence, and sometimes we can then skip our cells quite quickly in case there are no skeletal primitives inside. Of course, it can be that there is a skeletal primitive just near in the neighboring cell, and that we will need to take into account. So having some kind of a grid organization of which maintains the information of where our skeletal primitives are is very useful for acceleration of direct ray casting or ray tracing of implicit object representation. For our grid representation, we can also do the following. We can find out which of our grid voxels are containing the implicit surface. And we can use this both for direct rendering of implicit representations, as well as for the polygonization, which we will explain as the next approach. So imagine that we have we partition the space into a grid, and then we will have some skeletal elements. Let's say the skeletal elements will be here, and we can then look for where are our vertices, where our implicit object is still inside, and where are the vertices where we are already outside our implicit object. So we can evaluate the value of the function on the vertices. But imagine that we have a huge cube of vertices, and we do not want to evaluate it on every point, on every vertex. Therefore, it makes sense to start evaluating it on the vertices which are just nearest to the skeletal point. And then we find out that once we find that what is the value, we are still maybe inside. Therefore, we are going a little bit more further away along the gradient and find out, oh, we have now already reached outside of where we are outside the implicit object. And now we will basically mark all the cubes which are having mixed vertices, meaning some of the vertices are inside and at least one vertex is outside. Then we will have a cell in which inside there will for sure be the implicit surface. And once we have this information available, then we can visit the neighboring cells in order to evaluate where does the surface continue, and then basically go around all the surface and mark all the cells through which the implicit surface is intersecting. So now, once we define one cell, we can also, as we have defined here, we have one vertex is inside and another vertex is inside, another vertex is outside, and another vertex is outside. So we for sure have the implicit object surface inside this cell because it has mixed values. If all of them will be plus, it means that we are outside the surface. If all of them will be minus, then we are inside the object. But it still doesn't tell us too much about the actual geometry. Sometimes if our grid representation is too coarse, we might have not captured enough details in order to tell how does the surface exactly inside looks like. But we will know that there is the surface inside. And for the direct volume rendering of the implicit representations, we can then jump into this cell and perform the ray evaluation of the samples within this cell, because we know that the functional evaluation will be for sure within this cell defining as a surface at a particular position. And we want to visit all the cells which are having mixed signs, and we iteratively go along the entire surface and always mark the cells which we have visited already, so that we do not need to revisit them again. Such an approach is depicted here on the following picture. So we have just one skeletal element which is here, and we start with evaluating the vertices. So we start first here, then we go along the gradient, next evaluation, and then we will define the cell where we have mixed values. So this is our first cell with mixed values. And then we go along in one of the neighbors of the cell and find out whether we have, again, mixed values. And that's true, we do. So we mark this cell also with mixed values. We propagate furthermore until we find all the cells which have mixed values on their vertices. And through this, we can then use it for the, as I said, direct rendering approaches or for the polygonization. For the polygonization, the idea is that we will define, based on our 8 vertices of our, in 3 dimensions, of our cell, 0, 1, 2, 3, 4, 5, 6, 7 vertices. We will define which vertex is inside and which vertex is outside. So, for example, this information is encoded here. We have 8 bits, and each bit is defining inside or outside for information for our cell. So we can give a code to our cell in which will define what is its how is the surface intersecting this cell. So here we see that all of the values are inside, besides the least significant bit, the 0 here, will be already outside the surface. So the surface then needs to be defined somehow between these cells. We don't know exactly where it is, but we know that the surface will probably look like approximately like this, because this is already inside, and this is already inside, and this is already inside. So there is not really much more chance how the surface can intersect this cube. And we can, for each of these bit masks, define what is the constellation. How does the surface look like? Of course, it can intersect, for example, the line 0, 2. We don't know where exactly it intersects it, but we know that it intersects it somewhere. A logical thing would be to intersect it first in the middle and then evaluate what is the value there, and then refine further the intersection point. Or if we do not have time to compute it that precisely, we can just simply define that the intersection is the midpoint between these two vertices. We can see here the scenario as we described it, again with one vertex, the V2, being positive and all the other one negative, which defines us that we have to now have this scenario where the V2, V0 is intersected, V3, V2 is intersected, and V2 and V6 is intersected. Now, if we are interested in the value of intersection V2, V6, we would like to know where is the intersection on this edge. As I said, one approach can be that we define the midpoint. Another approach can be that we know what is the functional value which we are interested in. Let's say this is 0.5, and we don't know where exactly the value of 0.5 is intersecting this cube, but we know the value at the V2. Let's say the value V2 is 0.3, and the V6, let's say, is 0.9. So what we can do is we can simply approximate where the 0.5 will be by having the distance 0.9 minus 0.3 and the 0.5 minus 0.3 defining us. So how much is this? This is 0.2 divided by 0.6, so 2/6, 1/3. So our point A, we can approximate that it will be 1/3 on the distance from the point V2. So and we might further evaluate the value there and find out that we are, because this is a linear interpolation and our function might not be finding the value might not be found by the linear interpolation, and therefore we will need to use some numerical root finding method to find it more precisely. And once we have that, then we are basically defining our polygons, which are then, this is one constellation, but as I said, there are in fact 255 different constellations, or 254, where there is some intersection within the cell. And those are not unique. So there are 15 unique classes which we can organize our possible scenarios of intersecting the cube with a surface. So in total, we have 254 cells constellations which might be which are intersecting our implicit surface, but they are not unique. And the uniqueness can be defined by 15 different cases. So we have here one case, which is fully empty, which means that either we are fully inside or fully outside. So this is one class, which are already two different kinds, 0, 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 1, 1, 1. The second class is where we have one point inside and all other points outside, or the other way, one point outside and all other points inside. So there are, again, two different cases about inside-outside, plus we can have different vertices which have this different sign than the others. The point can be here, the point can be here, the point can be here, 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 and here. So therefore, we need to, a lot of cases are projecting onto this one class of polygonization. And then there are other classes where we have 2 points inside or 2 points outside, and they are defining as the same type of polygonization of our cell. This approach is called the marching cubes, where the cube is being polygonized based on the amount of positive or negative sign vertices. So here are all the different classes plotted. Once we have that, we want to know the more accurate intersection. Maybe it could be just in the middle, or we can find it through the linear interpolation as we described it on the slide before. For more precise, we can use an iterative approach if we have the computational capabilities to do so quickly enough in a desired time. We have also some kind of non-clear cases, ambiguity cases in our polygonization. And that is if, for example, these two are positive and we do not know whether the situation is that we have this kind of representation where we have these two triangles, or we have some kind of a wedge which is intersecting our cell. So which of them is correct? We can find it out based on the maybe making a sample in the middle of the face of our cell, and that one will tell us based on the sign whether it is the case 1 or the case 2, if the sign will be positive. So the 15 classes are not can be ambiguous, and therefore sometimes we need to have one more functional evaluation at the cell or face center to find out which case it is exactly. So this way we can generate a polygonal model out of our implicit representation and then render it with standard methods. Now, we have also different blending functions if we want to have the compositor, which is defining us what is the blend between the two skeletal primitives. Imagine, so this is called a generalized blending, a super elliptic blending, where if the n here will be 1, this will be simply an summation. So n equals 1, we have a simple summation. And if n goes to infinity, then we have the max function. So the higher the n is, the more it goes from a summation compositor into a max compositor. Max compositor means that we will simply create a union of the blending functions. So in case n is very high, imagine that you have the functional evaluation where this value, let's say fa is bigger than fb, then with n equals to infinity, the fa will become a very large number, while fb will go to will be smaller. So this large number will dominate, and then if we perform the square root, we will basically perform the square root mostly of this component, so it will be the larger number will be taken. So we will effectively be performing the max operation if the n is very large. If the n is very small, negative actually, then we will give the prominence to the number which is smaller, because with negative exponent, we are performing the root operation, square root or quadratic root, and so on. And with that, the smaller the number is, the less it is affected by the square root, and then that number will be then squared, or will be 1 divided by minus some value, minus infinity. That will be creating a very high value out of the value which sort of survived the square root more. And in case the FA is bigger than FB, in this case, the FB will dominate, and we will have the mean value of FA and FB, which means that the minimal value is actually defining as the intersection between A and B functions. In this image, you can see that when we are increasing our n, we are from summation gradually going more and more to a union operator, which we can see here that this is in very close to a union of two spheres, and the blend is having much more and sharper crease between these two skeletal primitives. The implicit representation nicely lends itself for use with constructive solid geometry. Maybe you remember the constructive solid geometry is an approach where we have some geometric elements, let's say some tetrahedron, maybe some cube here, and then we are performing, they are placed in a scene somewhere, and then we are performing some logical operator with them. Maybe we subtract one object from another, or we perform a union or intersection. And then the intersection can be further made to a union with another set of objects which are then in the scene. Maybe a sphere, a cylinder, and so on. So we can have various operators which are binary operators on the geometry. And the same we can do also on the implicit representations, both that the leaves will contain the actual geometry and the intermediate nodes contain the logical operations. The logical operation of union can be realized as the max function. So we are here talking about the compositing function, the one which was previously used as a summation. We can replace it with max function, for example, and then this will be a union of all the implicit objects in the scene. For intersection, we can have the min function. Let's have a look how this works. So if we have here two elements, now if I am now intersecting with my ray here, the max value, so this will be some value, let's say 0.5, f1 equals 0.5, and for f2, this value, f2 equals to 0, because this is the 2 primitive, this is the skeletal primitive 1, but with the union, I will therefore take the value 0.5, which means that I am part of this union. If I am interested in intersection, the minimal value will be taken, which is 0, which means that I am not having any surface at this position, because I am looking for values which are 0.5. If I will be intersecting with my array along this way, then all these points will be equal to 0, because one of these surfaces, for one of these surfaces it is outside, and only when for both surfaces we are inside, then we will be having the intersection, which is realized through this min operator. And then we can also have the difference operator, which can be then expressed as an intersection of A minus complement B. So complement B minus B is if this is our object, let's say this is B, all the space around is minus B. So that's its complement. And therefore, if we perform the intersection with its complement, then we are basically performing a difference, a negation of that object, which can be seen, for example, here. All right, so we have these logical operators, and we can then create our tree where on the bottom we will have our implicit functions, and then we will concatenate these with the logical operators and create the tree, which gives us the information on the overall geometry. Previously, we have defined our functional value by the distance from the skeletal primitive, the kernel fall-off function, and now we can additionally add one more function, which will be the warping function. So imagine that we have a function which will be just a spherical function. So we will have a skeletal primitive here, and we will have the implicit representation, which will be a sphere in 2 dimensions, a circle. But then we can have some kind of a warping function, which will change our function so that our values, let's say this would be normally the f equals 0.5, but this warping function along 45 degrees will scale this so that the value nu, so let's call it f nu, will be 0.5 here. And this will be, let's say, this position will be f nu equals, let's say, 0.8. So we are still inside. So with such a warping function, we can create an deformation of our implicit objects. This warping function can be also time dependent, and through this we can create some kind of animation. One needs to keep in mind that this warping function stores basically an inverse of the warping. So when we are performing the ray intersection, let me just delete this. When we are performing the intersection with our implicit surface, we would like to know along our ray where is the value 0.5. So, and here when we will be intersecting with the sample, here will be 0.5. If we will be continuing because our representation is transparent, then we can sample furthermore. And at this position, we will have the value 0.5. So it will sort of scale the value. It will tell us that I am the value which you would find at this position. It's an inverse warping. It's not that we are informing how to get from a point on the surface to a new point, but from a new point, how do I get to the old surface? That's what the warping function is storing. We can have further deformations. For example, one of the deformation functions can be defining as a twist. So we can see this is a z-axis here, and the z-axis is, so the z value is unchanged, but for the x and y coordinates, based on the z, we are performing some rotation. The x and y coordinates will both change through some cosine and sine functions, of an angle function, which is parameterized by the magnitude of z. So basically, you can put the theta z is equal to z, for example, or you can maybe maybe scale it as a z pi or something like that. So this is one deformation function which we could use. Another deformation function can be tapering, so that we are tapering our implicit representation, and the scaling is again a function of z. So along the z-axis, we are not scaling anything. There is no contraction going along this dimension, but there is a contraction along this direction, for example. So this is, for example, another warping function which can be applied on the top of the distance function or distance evaluation and the kernel function, which form the functional value of our implicit representation. And if we put all these together, we can create an interesting implicitly defined scene. So here there are several elements, and we are putting them together through the we are first performing certain operators on them, like for example, here is the tapering, and here we perform a blending operation, meaning the summation. Here is some kind of a twist warping function from a otherwise a rectangle skeletal primitive, and so on, so that we can create first some simple combinations of our implicit representations and put them together through blending or through union or through intersection. And this way we can generate quite effective complex geometry of a staircase, for example. This staircase is nicely blended together, as we can see here. And in this scene, you can see that all objects are pretty much defined by the implicit representation. Implicit representation can be also UV parameterized for texturing, as we can see it here. Several textures have been applied to our implicit objects here. But one needs to say that for man-made objects and man-made scenes like houses, interior, and so on, the implicit representation results in some kind of a bulky, blobby representation. So it might not be the optimal one, and it takes a long time to calculate. But for natural phenomena, implicit representation would be often the winning strategy. From a modeling perspective, it will be also very popular because with these implicit objects, you can create smooth surfaces very easily. And that is all for today. Thank you very much for your attention on the lecture on implicit representation, and I'm looking forward to see you at the next lecture.